You can break the monitor down into 7 different monitor circuits, or 7 different monitor sections. Section number 1, the power supply. In the monitor, there's a regular power supply. It's a linear power supply with the series pass regulator circuit, really simple circuit. The power supply, remember that's called the B+. Depending on the model, will be anywhere from about 100 plus 115 to about 130 volts DC or so, depending on the type of monitor that it is. Section number 2 is the video circuit. Remember the video circuit? That's the red, green, and blue, the colors. Number 3, the blanking circuit. Remember that turns off the guns during the retrace time so that we don't get the vertical retrace lines and so on. Section number 4 is the sync circuit. There's really a couple of different sync circuits, but let's just call it one. Is the picture rolling? Is it shifting left and right? That would be a sync problem. Number 5, vertical deflection. Obviously, that makes the beam move up and down. Section number 6, the horizontal deflection. And last, and definitely not least, here I'll put it in danger, warning, safety red, the high voltage circuit, or the high voltage unit, really. The high voltage, by the way, is sometimes referred to as the EHT. In Europe, they call it EHT, stands for extremely high tension. I guess that's how they feel at the time that they're working on that circuit, very tense or something like that, I don't know. But you can break the monitor down into these 7 different circuits. When you're working on a monitor, and you have a problem with the monitor, the best way to troubleshoot it is to look at the way the monitor is put together. Look at the different sections and eliminate anything that cannot possibly be the cause of your problem. Whatever's left, you test. Let's go through some possible problems, and I'll show you what I'm talking about here. Get my stupid fingers in here. Now, don't say anything. This is a real simple one. Don't say anything yet. It's pretty obvious what's wrong with this one. As soon as it warms up, that is. Don't say anything. It's really obvious what's wrong with this one. Okay, now let's take a look at these different monitor circuits. All right, is this a high voltage problem? No way. Why not? You see something on the screen. If you see anything at all on the screen, you definitely know the high voltage is okay. So we've eliminated that. It's definitely not a high voltage problem. Is it a horizontal deflection problem? No way. Number 1, you got a horizontal line there. Number 2, though, there's another reason, a real important reason why you know that it's not a horizontal problem. In the monitor, the horizontal deflection circuit actually drives the high voltage unit. Well, that's pretty interesting. In the monitor, the same circuit that makes the beam move left and right, which obviously it's doing here, also drives the high voltage unit in the monitor. Remember I was asking you if you could hear that high-pitched squeal that a monitor makes? Well, that squeal is really coming from the high voltage unit itself. That sound, that high-pitched squeal, is actually coming from this high voltage unit. Whenever, not this one, but the one in the monitor. Whenever I turn on a monitor, I always listen for that squeal. If I can hear that high-pitched squeal, it means that I have high voltage. I always listen for that. It means that I have high voltage. And if I have high voltage, what do I know about the horizontal circuit? It's got to be working okay, because the horizontal drives the high voltage. So this is definitely not a horizontal problem. In fact, as soon as you eliminate high voltage, you eliminate horizontal. Let's see, is it a power supply problem?
No.
Hell no. If the power supply was bad, we wouldn't get anything at all, probably. Although there may be a few minor power supply problems I'll talk about later, but it wouldn't cause this problem. Is it a video problem? No. Is it a color problem? No. And you can see that when I change the pattern generator, you can see that it's changing color. So obviously it is not a video problem, so that's okay. Is it a blanking problem? No, because that would cause you the retrace lines. You'd see that. Is it a sync problem? Maybe a sync problem? Vertical sync? Horizontal?
No.
Nah, way. When you have a sync problem, you have a whole picture, don't you? It's just rolling or shifting. What's left? Sure. You have no vertical deflection here. You have no vertical deflection whatsoever. Remember, the vertical deflection is the thing that fills the screen from the top to the bottom, and it's just right down the middle. So this is a simple problem, no vertical deflection.
Yeah, but if you don't have the rest of your picture, how do you know you don't have sync?
What are the chances of two completely separate circuits failing at the same time? You probably won't. So this is no vertical deflection. Well, once I know that I have a problem where I'm missing vertical deflection, let's say in this case, now I turn off the monitor. And using my meter, I test the parts in the vertical deflection circuit. And as we'll see later on, in most monitors, there are only two transistors in the vertical deflection circuit. They're called the vertical output transistors. I'll show them to you later on. Output transistors fail a lot, and in this case, vertical output transistors are a fairly common failure. By doing it this way, I do nothing with the power on. In fact, the only test I normally make with the power on in a monitor is checking the power supply voltage, the B+, to see if it's good or not. And of course I'll show you how to do that as well. But when I get to a monitor like that has this problem, I know, first of all, I know by process of elimination that it's none of these other things. It's definitely a vertical deflection problem. So I don't even care where these other parts are. I don't care where any of this other stuff is. I know it's all working okay. That's not my problem. All I have to do is find the parts in the vertical deflection circuit, and safely, with the power turned off, I check the parts in that circuit. Does that make sense? And we'll go through those circuits later on. Let's take a look at this problem. Now look at this carefully. Remember what the color bars looked like before. Okay? And this would look pretty much the same in a regular video game. Jeff, what's our problem here?
Plus your green and red.
What's our problem here? No red. We have a red problem. There's no red. This is supposed to be blue, red, magenta. Remember that? I've got blue, black, blue. This is supposed to be yellow. It's green. Yellow is red and green mixed together. And all it is green. I'm missing red here, and I'll show you later on an actual video game what this looks like when you actually see the picture on a video game. It's missing a color. But here we're obviously missing the color red. Well, this ain't a high voltage problem. It's not horizontal, not vertical, not sync, not blanking, not power supply. We know it's a video problem, definitely. Not only do we know it's a video problem, but what do we know about blue and green? They're fine. They're perfect. So now, not only have I eliminated it down to 1/7 of the monitor, meaning the video, but I've eliminated it down to 1/3 of that circuit as well. just by looking at this monitor, I know that I'm missing red. I have a red video problem, and as we'll see later on, there are usually only 3 transistors in that circuit that control the red. It's going to be one of those 3 transistors. The chances of it being anything but that are very, very slim. You might also see a problem like this, or like this, or like this. No. Now you might think it is because you see a blanking problem because you see the retrace lines, but if I bring some kid off the street and say, "Hey kid, come here, what's this?" He's going to go, "Oh, it's blue, mister." Right? It's blue. It's way, way blue. Or it's green. Let me just crank up the brightness so we see the other colors here. It's blue or green or red. Now, this is a video problem. This is a color problem. Do not look at a problem like this and say to yourself, "Oh, I'm missing," let's say like this, "Oh, I'm missing red and green." Or a problem like this that's very green and say, "Oh, I'm missing blue and red." Or like this and say, "I'm missing green and blue." Those colors are there. The problem is that you have too much of a color. So much that it overpowers the other colors. This also has to be a video problem. And as a matter of fact, and we'll look at this later on, this has to be one of the 3 transistors on the neck board. On the neck board of a monitor, you'll almost always see 3 transistors. You see them here as one here, here, and here. These are the video output transistors, they're called. Video output transistors. And it's a fairly common problem. And we'll talk more about this later on when we look at the other circuits. That also is a color problem, but in that case you're not missing a color, you have too much of one color. Okay? If you have a sync problem, of course, the picture will roll as I demonstrated, or shift left and right. That's easy. If you have a blanking problem, and that's difficult for me to demonstrate. If you have a blanking problem, what you'll probably get is this, a blank screen. Get it? Blanking, blank screen, some kind of cosmic connection there, right? You'll probably get a blank screen, and then if you go to turn up the brightness, you won't get any picture at all. You'll just see raster with the vertical retrace lines on it. It's difficult for me to demonstrate this on this particular monitor. The difference between the blanking problem and the video output transistor problem that causes the solid color screen with the retrace lines is that you have one color when it's a video problem, red, green, or blue. If you have a blanking problem, blanking turns off all 3 guns at once, and so naturally it looks white. Because can you see that when you break the monitor down into its 7 different sections, it's usually pretty darn easy to look at the monitor, see where your problem is, then you don't have to test all this other stuff, you just go for whichever section is bad. Now that we know how the monitor works, let's take a look at the sections one at a time. Let's take a look at the video circuit, see how the video section works. Now remember the way this section works. We've got the computer board that's sending out the red, green, and blue signals. The video signals to the monitor. And of course the return path, the video ground comes back the other direction. Well, these color signals are not powerful enough to drive the electron guns directly. The electron guns that are in the neck of the picture tube here require about 180 volts or so to operate, depending on the monitor. Some are more, some are less. And the voltage coming out of these things is only 4 or 5 volts or something like that. So somehow this has to be amplified. Somehow we have to take the video signal that comes out of the computer board and amplify it. So inside the monitor, there are 3 amplifiers, and we use a triangle as a symbol for an amplifier. And these are just made out of transistors, and we'll take a look at the actual circuit in just a few minutes here. And these color signals, these video signals, go into these amplifiers. The amplifiers amplify it, and it's the output of the amps that drive the electron gun to make the electron shoot out. Gee whiz, guess what we call these amplifiers? That take the video signal and amplify it. Video amplifier, sure. There are 3 identical video amplifiers in the monitor. The 3 identical amplifiers, one for each flavor, one for red, one for green, and one for blue. Now, let's say that you got to a game and you were missing a color. Say, for example, you were missing the color red. Well, if you're missing a color, chances are pretty darn good that it is a monitor problem. But maybe it's not. What if the board is not putting out the red signal? What if the red video amplifier is bad? What if the wire is broken? The first thing we have to do is figure out where the problem is. Is it in the board? Is it in the monitor? Well, there's several different ways to do this. One of the easiest ways is to simply measure the voltage at the video input of the monitor. Measure the voltage right at the connector. After all, it's just a changing voltage here, right? So we can do that pretty easily. Down here is the video connector. Remember we looked at that before. Well, all we have is some changing voltages here. And we can measure those with the meter. And actually you can measure this on AC or DC. It doesn't make any difference. You'll get a couple of volts out of it. And here's what you do. Just set your meter to read AC or DC volts, like 2 volt range. Ground the black meter lead to the chassis. Just find a hole somewhere, I showed you before, a hole somewhere in the chassis where you can put the meter lead and just leave it there. In this case, the meter lead's just sticking in that hole right there. Then put the red lead in the connector. Now, we're pretending that we're missing red. So that's the red pin right there. Right there. And the meter, you see something on the meter. In this case, is 1.4 volts. It doesn't actually matter if you have it on AC or DC. If I switch this over to AC, I see a couple of volts of AC. I see some voltage there anyway. That's the main thing you're looking for, some kind of voltage. Now watch what happens here. Let me put it back on DC. All I'm doing is measuring the voltage at the red video input. Do we have it? Obviously we do. If I was missing red on the screen, then it wouldn't be the computer that was at fault, would it? Because I know I have the voltage. Watch what happens as I change the pattern on the screen. As I change the pattern on the monitor. Now I've got so much red, I've actually got to go up a scale. I've got 2.5 volts. Look, the whole screen's solid red. You know, so that makes sense. Let me just focus here. I've got a green screen here. The red's not really on. I'm not sure why it says 0.2 even. Maybe there's some residual voltage coming out. Blue, there's no red there. That has some red in it, but it doesn't have very much, does it? You know, the screen is mostly black. So I get 0.39 on the meter. There's even less. The meter says 0.2. Just some dots on. White is the red on all the way, 2.5 volts. And the color bar, there's not red everywhere, so it's about 1.4 volts at this point. But all you have to do to tell where the problem is simply measure the voltage at the video input here, right at the connector, whatever pin you happen to be, where the problem is. If you have the voltage there, you know the board's okay. If you don't have the voltage there, then obviously the problem isn't in the monitor. The reason you're not seeing anything is because the voltage isn't there. Does that make sense? That's pretty important. Now here's another quick way that you can do it even without using a meter. Let's say we're missing red, but you know you have green and you know you have blue. You see them on the screen, and you see the green and blue, so you know the amplifiers are good. You can swap the wires. It's really easy to pop the wires out of the video connector. You could take, for instance, the red wire and run it into the green input. Let's say you're missing red. Nothing on the screen. Which is it? The board or the monitor? Well, if I take the red output from the board, which I don't know whether it's good or bad, and I put it into the green amplifier that I know is working okay, look at the screen. If I see green, that tells me that I have a good signal, doesn't it? Now, it's not going to be red because this electron gun's pointed at the green phosphor, obviously. Now, likewise, or conversely, I should say, I could take the green output and run it into the suspected red amplifier. If this green is good, right? I know because I saw green on the screen before. If I still don't see red, then I would know that the monitor's bad. Now, to be quite honest with you, if you are missing a color, chances are extremely good that it will be a monitor problem. A missing color is hardly ever a board problem. But it might be. For instance, I did a class in Salt Lake City, and this guy brought a poker game in, and the problem with the poker game was that there was no blue. Well, in a poker game, really, it's just the background that's blue. There's really not any blue in the actual display, so it was still usable. But he had brought this game apparently to several people. Nobody could fix the monitor in it. The first thing I did was swap the blue and the red wires. And I fired it back up again, and I got blue hearts and blue diamonds. Blue hearts and blue diamonds. That's Lucky Charms. So obviously the monitor was working. The blue was okay in the monitor. No wonder nobody could fix the monitor. There wasn't nothing wrong with the monitor. How stupid is it to spend a bunch of hours working on a problem that doesn't exist? So when you are missing a color, you should always swap the wires, or at least measure the voltage first. Make sure that you know where your problem is. If you have too much of a color, that has to be a monitor problem. If you have too much color, the bright screen with the retrace lines, that has to be a monitor problem. There's no board failure that can do that. But missing a color, then you really need to determine where the problem is. Make sense? All right, well then let's start taking a look at the schematic diagrams. In the back of your book, the last pages of your book are the schematic diagrams for the monitors. Let's look at the very back page, which is for the electro-home monitor. We'll have a chance to work on some of these electro-home monitors tomorrow because Jeff Stern brought some of them in. It's kind of nice. I like to use the electro-home monitor because, number one, there's millions of them out there. There's just a lot of electro-home monitors out there. Number two, the schematic diagram's pretty straightforward. We'll look at this one and we'll look at some others as well. Well, let's take a look at the video circuit. And if you look at the top of the schematic, right up at the top where it says blue, green, red, up there, this is obviously where the video comes in. The red, green, and blue signals come in. And if you just kind of casually follow the red wire down and to the right, it goes into a circuit made up of transistors X101 and X102. I just want you to see that they exist. I don't care, let's not look at it in any detail right now. Go back up to the green wire, where the green wire comes in the middle, and follow that wire straight down and to the right. Do you see how it goes into X103 and 104? Go back up to the blue wire now, follow the blue wire straight down, hang a right, X105 and 106. And all I want you to see is, can you see that you have three identical circuits here? I mean, even if you don't know anything about electronics, if you're just thinking of it as some interesting squiggles and lines, obviously we have three identical circuits here. That being the case, let's look at one. Let's just look at the red circuit. So go back up to the top where the red wire comes in and follow that down and to the right. And it goes up a little bit through a capacitor and a resistor into the base of X101. Well, that makes sense because the base is the input of a transistor, isn't it? So it makes sense that the input comes in there. The output of X101 comes off the collector, the lead on the top, the lead without the arrow on it. And follow that to the right. It goes through a small resistor, 680 ohms, and into the base of X102. You may notice that X101 is NPN, X102 is PNP, opposite polarity. Well, X101 and X102 form the video amplifier. And I can tell that because, number one, the color comes into it, so that's obviously the video amplifier. But number two, on the top of the schematic, it does say video amp right there on the top of the schematic, so it's kind of hard to miss that. And it even gives you the part number, 2SC454 or 2SA673, depending on whether we're talking about the NPN or the PNP transistor. The output from X102 comes off the emitter. That's the lead on the top, the lead with the arrow on it. And if you follow that out to the right, it actually leaves the main printed circuit board. You see the heavy dashed line around most of the schematic? That's the main printed circuit board. That's this part. That's this main part of the printed circuit board right here. It leaves the main board through this connector, through this cable, and goes up to the neck board, what we commonly call the neck board, where the three video output transistors live. So if you follow that wire from the emitter of X102, goes to the right, leaves the main board, jogs down, hang a right, it goes kind of up into the circuit that is X102 on the neck board. So, how many transistors are there for each color?
Three.
Totally three, right? Two on the main board and one on the neck board. And here's the video input connector right here. And those video amplifier transistors are these little black transistors that surround it. All these little guys here. These are the video amplifier transistors. Kind of dusty. Hard to see. But for instance, there's X105 right there, and so on. And I showed you this before. From the bottom of the board, it's real easy to spot which transistor is which. You know, for instance, here's X102. X102, you know, here's the base of X102. Here's the collector of X102. So it's real easy to tell which transistor is which. Then, after being amplified by the video amplifier transistors here, it comes in here, amplified by a couple of transistors here, then it goes up through this connector right here, and you can see the red, green, and blue wires on it, see? Red, green, and blue wires. And then it goes up through this connector, through this cable I should say, up to the neck board. And there's the three video output transistors on the neck board. One for each flavor, one for red, one for green, and one for blue. So that's pretty simple. Here's a cool little shortcut. This connector, most monitors have a similar connector that carries the amplified signal from the video amplifier transistors through this connector up to the neck board. If you disconnect this connector, the transistors on the neck board will test perfectly good in circuit. Because essentially you're taking them out of circuit.
Right.
When you're dealing with color problems, you have one really cool advantage. You do have 3 identical circuits there. Absolutely identical. If you have a problem with a color circuit, and you're testing, let's say you're testing a part, and it checks a little weird in circuit, like it doesn't check exactly perfectly normally, compare it to the other transistor that's the same thing on the other color. Even though it checks a little weird, if they all check the same way, that's normal, isn't it? In other words, if you look at the schematic diagram, let's say you're checking X102. That's the red amplifier, not the one on the neck board, on the main board. All right? And it checks a little weird in circuit. Well, compare it to X104 and X106. They're the same part, aren't they? If they all check exactly the same way, that no matter what you're reading there, that's normal. In fact, what I usually do, instead of doing the whole transistor test, if I want to compare one to another, I simply go, for instance, base to emitter on 102, 104, 106. Are they all the same? Yeah. Instead of doing the whole transistor test and trying to remember what you got on each reading, just go base to emitter, 102, 104, 106. If 104 and 106 are the same, but 102 is completely different, obviously you found your problem. On the other hand, if they're all the same, then that ain't bad. That's normal for in circuit. Not only that, if you get really, 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 really confused for some reason, like you've just had a terrible day, but you've got to fix this monitor, you can also try swapping components. You can try swapping parts. For instance, if you think transistor X102 is bad, but you've lost your meter or the dog ate it or something else, swap 102 with 104. If the red problem all of a sudden becomes a green problem, then obviously that part is bad. And I've had to do that on occasion, not on this particular monitor because it's so simple, but in the Hunter X monitor we had a color problem in one of our labs that wasn't a transistor. Very unusual. Usually it's a transistor. It turned out to be a capacitor. Well, one at a time we started swapping the parts in between the channels. We moved the capacitor and all of a sudden the red problem turned into a green problem. Okay. Anyway, now I'm really confused. All right. So you have 3 identical circuits. If necessary, you can always swap the parts between them. You should never have to do that. The video problems are so simple. Let's take a look now at this exact monitor, the Wells Gardner 4900 series. That's on page R34. A very popular monitor. This is also the monitor that's in Iron Man's Sky Shark game. And it has a capacitor failure, which we'll fix later on. Let's take a look at the color circuits in this monitor, shall we? And if you look at the top of the page again, where it says red, green, blue, follow the red wire down, left, down, down, left, down. Find Q203 there. Q203. Everybody with me? Anybody not see that?
207?
203.
Yeah, got it.
203. Okay, Mike, you see it? It's right up here. Okay. 203. Q203 and the transistor right underneath it are for the red video amplifier. The transistor right underneath Q203 is Q206. Do you see just to the left of the transistor where it says Q206? This is kind of a screwball schematic in that respect. Don't get confused. 203 and 206 are a pair. Right next to it, 204 and 207 are for the green. And 205 and 208, correct, are for the blue. So sometimes you got to be careful. Schematics are a little tricky. They're drawn by human beings, and human beings screw up sometimes. In this case, I guess he just kind of ran out of room. In any case, it's pretty obvious that there are 3 identical circuits once more. That's pretty obvious. Now, go over to the right-hand side. Let's look at the neck board. It's real easy to identify the neck board. Look, it's attached to the picture tube. I mean, that's what could be easier than that. And there are the 3 video output transistors. Q401, the red output transistor, 402 is the green output, 403 is the blue output. So, same thing. I mean, what could be easier? If you got a color problem, you got no problem at all. Does this make sense so far?
Yeah, I don't see how those first two pairs of transistors are linked together.
The first three pairs, you mean?
Yeah.
Well, do you see how their emitters are tied together? Through a couple of resistors?
Yeah, you could. Oh, it's numbering, I get
The numbering's offset to the left.
Yeah, the bottom transistor is labeled to the left of the transistor.
Okay, yeah.
Yeah, very confusing. If I had a red problem and I didn't know this, the first thing I'd check is 203 and 207, wouldn't you?
Yeah.
I mean, that's the way it looks, but that's not the way it actually is. That's not the way it actually is. So anyway, same thing, 3 transistors for each color. Should be no problem whatsoever troubleshooting something like this. Now, occasionally you'll find that your color problem is a bad picture tube. Bad picture tube. And a bad picture tube with a color problem can cause a couple of different kinds of problems. It can cause you to be missing a color, or very weak, or it can cause way too much of a color, like intense green, blue, or red. Remember, I demonstrated this to you before. When you have like a color that's real bright, it overpowers the other colors, right? If you have this problem, you should go right for the neckboard transistor, because that's the only thing that can cause this problem. You should go right for the neckboard transistor. Now, as a matter of fact, I always start with the neckboard transistor regardless. I start with the neckboard transistor regardless of whether the problem is missing a color or too much of a color. And the reason I start with the neckboard is that it's right there. When you open up the game, the neckboard is, to open up the back of the game, the neckboard is right there staring you at the face. And remember that I don't bother discharging the CRT. Remember that? I don't have to discharge it. In fact, I don't even have to take it off the neck. Open up the back of the game, and here you see the monitor just staring at you in the face. And when you look at the neckboard, there's the video output transistors. See, you see them right there, Q402, see, Q401, emitter base collector, Q403. They're all right there. And I don't even, in fact, it's convenient that this thing's mounted on the neck. I don't even have to take it off the neck because it holds it up for me so that I can test it adequately. So, I can touch it here. Yeah, the picture tube's charged up, but it's turned off, of course, and I can test all the transistors. So, if you have a problem where you're missing a color or you have too much of a color, those can both be caused by the neckboard transistor, so I always start there first. Now, if you have the problem with the too bright of a screen, real bright color in the retrace lines, it's really almost always going to be the video output transistors. But it may be the picture tube. It may be the picture tube that's bad. Here's how you can tell. You get to the monitor, you've got a real bright screen, you check all the video output transistors, they're all perfectly okay. Find the video output transistor that's associated with whatever color your problem is, green, blue, or red. In this case, 401, 402, or 403. Unsolder, remove the transistor, put the neckboard back on, fire up the monitor. If you still have that incredibly bright color and the transistor's gone, the picture tube has to be bad. You can fix it, probably. Believe it or not, there's a pretty good chance that you can fix the picture tube. And here's how you can do it. This is a really neat trick. This trick has enabled me to fix a lot of picture tubes. About 30, maybe 40% of the bad picture tubes that I've had where the color is way too bright like that, I've been able to fix it. And here's how you do it. Inside, first of all, let's understand what the real problem is. Inside the electron gun assembly, the electron gun, each electron gun actually looks like this. It's like a cylinder. And I'll do it in a different color here. Coating the top of the cylinder is a substance known as barium oxide. You don't really have to know what it's called. But there's this stuff called barium oxide. It is a coating that they put over the cathode, the thing that emits the electrons, that helps it emit electrons. It won't emit electrons by itself, though. It has to be heated up. And the heater actually goes up inside the cathode like this. And this is just the part that you see glowing is the little part sticking out the end. But most of the heater is up inside this thing. And when the heater works and it heats up the barium oxide, that's what causes the electrons to come off. That's our source of electrons. And then they're accelerated by the gun and they spit them out. Well, what happens is a tiny bit of some kind of schmutz floats down there and shorts the electron gun, the cathode, to the heater. It's a heater to cathode short is what they call it. And it may be just a little piece of metal that's flaked off the inside of the cathode, or it may be something from elsewhere in the picture tube. This is especially common in cocktail table games, because in a cocktail table game, the picture tube is facing like this. Or in the gun games like Operation Wolf, Mechanized, those ones that where the monitor's horizontal and you're looking in a mirror, the monitor's like this. Well, any crud that flakes off the inside of this thing lands right down here in the electron gun assembly and screws it up. So that's what we're trying to get rid of. That's what causes the too bright of a screen. Here's a couple of different ways that you can do it. There's 3 different things you can try. Number 1, you can turn the monitor like this. Nice picture tube. You can turn the picture tube like this, face down, and gently, oh so gently, with a screwdriver. Screwdriver.
Right here?
Sponge. Thank you. Gently, oh so gently. Tap on the neck of the picture tube. Just tap it with the handle. I mean, really, because you saw what happens when I pass that electron gun around. That's what happens if you're not gentle. Tap it. You may be able to get that piece of junk to flake out and drop out. I'm not real successful doing that, but I'm able to fix a few of them that way. The other thing you can do is this, and this isn't written down anywhere in your book, by the way, so you really want to pay attention to this. Let's go back and take a look at the neck of the picture tube. If you look at the neck of the picture tube, things are usually labeled here. For instance, here's the heaters, pins 9 and 10. See what says H for heater? Right? Heater, pin 9, pin 10. The cathodes, the green, blue, and red cathodes are here. And they use the letter K for cathode. This is green cathode, KG. KR for red cathode, cathode blue, KB. The reason they use K is that there's this thing called a grid I mentioned before. For instance, G2 is the screen grid. And they just didn't want people to get confused between C and G. So they use the letter R for K for cathode. So that's the red cathode, KB is the blue cathode, KG is the green cathode. Well, G2 is the screen grid right here. Look at it carefully. G2 is the screen grid. What we're going to do is momentarily short out between G2, the screen grid, and the offending cathode. Here's the cathode connection right there. G2, the screen grid, we can make that have up to 1,000 volts on it. You crank the screen voltage all the way up. Crank the brightness all the way up, the screen control all the way up. And momentarily, and I'll show you in just a second, we're just going to take a little clip lead and short between G2 and whichever cathode is bad, whichever one is on way too bright. What that does is it blows away the short circuit. It blows away the little bit of whatever it is that's shorting the two out. Well, here's how you do it. Let's pretend that we have a red problem where the red is stuck on all the time. You see G2 and KR there. The first thing you do is turn up the screen control. Here's the high voltage unit. You can clearly see through the dirt here, screen. The top one's always focused, the bottom one's screen. First thing you do, crank that screen control all the way up, maximum, all the way to the right. That's going to put maximum voltage here on G2. Then, using a clip lead, and be careful here because you're dealing with 1,000 volts, momentarily short G2, it's difficult to do here, G2 with the cathode. Just momentarily short the two together. I'm shorting grid number 2, the screen grid, to the cathode. Just keep tapping it on there. The first time you tap it, it may blow the short right away, and then the screen will go dark, which is what you're hoping for. If it doesn't work, just keep doing it. Do it a couple of dozen times. If you try it a couple of dozen times and you never get it, and it's still bad, then of course that's not working. But usually what will happen is you get to the monitor. Well, here's from start to finish. Here's what happens. You get to the monitor. Wow, that screen is green as hell. Holy cow. I think that the green video output transistor is bad. Turn off the monitor. You check the green transistor, test perfectly. You compare it to the blue and red just to make sure they all test the same. Maybe even you really get freaked out and you swap the green and red video output transistors. You still have too much, what did I say? Green. Okay, too much green. So you think, well, I guess the picture tube's bad. You remove the video output transistor for the green color. You got it sitting on the desk right here. It's out of the circuit. You turn it back on. It's still too green. Picture tube is bad. Crank up the screen control. With the power on. Do your little short circuit thing. Tap, 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 tap. All of a sudden, bam, it goes dark. No more bright green. You got it made in the shade, hopefully. That works really often. That works a lot. It works surprisingly a lot. The first time I ever did that, it just blew my mind. You should have seen the little dance I was doing around the shop. It was like unbelievable because you just saved $150 and a whole bunch of time because that's how much a replacement picture tube costs. Okay, G2 and whichever is the bad cathode. G2 is the screen grid. If you forget how to do this, just give me a call. I'll be glad to tell you about it. And anyway, so. Also, one important thing, make sure that the video output transistor is out when you do this. Because you're putting 1,000 volts on that circuit, the output transistor is probably only a 200 or 300 volt transistor. You may blow the transistor. But you have it out anyway, don't you? You've pulled it out to determine that the picture tube is bad. Dan, you cool? Okay. So that's a pretty cool deal. Now, if that doesn't work, don't give up. There's still something else that you can probably do to fix it, especially when you have this problem where the gun is stuck on all the time. Most TV repair guys have a piece of equipment called a CRT rejuvenator, commonly called a tube shooter. And it's just a piece of equipment that does, in a much more sophisticated way, what we just did here. That is, it charges up some capacitors and really, bam, puts a blast on that thing. And actually what it will really do is heat up the filament real hot as well, and then, bam, blow it away with a big, very controlled charge. If you don't have a CRT rejuvenator, which you probably don't have, you can usually take the picture tube. You only need the picture tube. You don't need the whole monitor, although you can bring the whole monitor there. Take it to a local TV repair guy, and he should shoot the tube, as it's called, for $5 or $10. The whole process only takes 5 minutes of his time. If he wants to charge you more than that, well, shine him on. Just call around, call a bunch of places, say, hey, I'm in the video game business. Can you shoot this tube for me? And how much will it be? He will probably warn you that, and this is true, that there's a good chance of completely destroying the tube when you try to shoot it. Because sometimes it just completely wipes it out. But it's wiped out anyway, as far as you're concerned. It's useless anyway. That gun is stuck on all the time. So don't hesitate to do it. But my point is, never do this on a working tube. Never just say, hey, let's shoot this good tube, see what happens, because you might blow it. You'll see, when you shoot the tube, you'll see a little spark down here inside the neck, which is the arc that's trying to blow the short away. Okay? So just because you have a bad picture tube doesn't mean you have to throw it away. When I think of the tubes that I did throw away before I discovered this little trick, it really pisses me off. If you have a tube where you don't have enough of a color, like enough red, enough green, or enough blue, and it's not and it's not the monitor. That is, you know it's the picture tube. And of course, the easiest way to figure this out is by swapping chassis and see if the picture tube is bad. You can also ask the CRT rejuvenator guy, the TV repair guy, to do the same thing. It's a slightly different process. In that process, they heat up the cathode really hot and leave it on for a while, and it boils the crud off that coats the barium oxide. It gets like crusty covering on it. It blows that away with a more controlled pulse. There's like 3 different levels of rejuvenation: low, medium, and high. You start with low, you try that, medium and high. That works really great. I have an really old CRT rejuvenator. It's about 20 years old. I had to put different sockets on it for today's picture tubes, but we had an APB, Atari APB, come into the shop. The picture looked terrible. It was all faded out. You could barely see the picture. That's one of those medium resolution monitors, a special monitor. It's a special picture tube and everything. To replace the picture tube was going to be about $400 or something weird like that. The game ain't worth it. There's no way that game's worth it, and with that monitor, you can't convert it to anything else anyway. So I used the CRT rejuvenator on it. Man, it worked really great. I ended up with a beautiful picture. It worked. Okay, let's take a look at the blanking circuit, shall we? Let's look at the blanking circuit in the Electrohome monitor. Turn to the last page in your book. Let's take a look at the blanking circuit. If you look at the neck board, look at the 3 video output transistors, and you may notice that the bases of all 3 transistors are tied together. If you follow that wire kind of down and to the left, it leaves the neck board, and follow it over and up and all the way to the left, and find transistor X304, the blanking transistor. Anybody not see that? I'll point it out to them here. Blanking transistor. The blanking transistor activates during the retrace time. During both the vertical retrace and the horizontal retrace, this transistor X304 is turned on. Well, if you check this out, look, the collector of this transistor is connected to all 3 bases. And the emitter of this thing's grounded. When this transistor activates, it shorts collector to emitter, doesn't it? That's the way transistors work. What happens to the voltage on the base of all 3 transistors? It drops to 0, doesn't it? It grounds it out, in other words. The base of all 3 transistors goes to 0 volts as it is shorted to ground through this transistor. It's a ground switch, isn't it? Like we saw before. It's a ground switch. It simply grounds out the bases of all 3 transistors. Well, if there's no voltage on the base of the transistors, are the transistors on or off? They're off, aren't they? Of course, they're off, and that's what turns off all 3 electron guns all at once, which is what we want to do during blanking, huh? That's the idea. The blanking circuit's supposed to turn off the electron guns so that we don't see the zigzaggy vertical retrace lines on the way back up. Now, when this transistor fails, as most transistors do, it shorts collector to emitter. The result is that blank screen thing that I was telling you about. The screen is blank. So you get to the game coins up, makes all the game sounds, as we discussed before, and it's definitely a monitor problem. You reach in the back, you turn up the screen control, but all you get is raster and vertical retrace lines. No video, no actual picture. You do get brightness, you get the raster, you get the retrace lines, but no actual picture. You're looking at a blanking problem. And in this monitor, it would be X304. Or, if you look at the schematic diagram, right next to X304 is another transistor, essentially connected pretty much the same way, isn't it? X303. It's called the beam limiter. It's only in this particular monitor. It's only in this Electrohome monitor. If it fails, it does the same thing. It shorts collector to emitter. I've seen it happen a few times. In fact, I've seen them both fail on occasion. And so it keeps all the guns turned off all the time. And the only way you get any brightness at all is by cranking the screen all the way up. And you'll get the raster with the retrace lines, but you won't get anything else. No actual video. If you look on page R34, turn to page R34, that's the Wells Gardner 4900 series. That's the one that we have up here. In the upper left-hand corner of the schematic diagram, the upper left-hand corner, you see the two transistors Q201 and Q202. They're not labeled. They have something to do with the blanking circuit. It's handled in a different way in this monitor. The blanking is done a little bit differently in this monitor. Never, ever, never seen these fail. You'll probably never see them fail. I never have, anyway. Let's take a look at the sync circuit now. And as long as we're on the same page here, look up at the top, just to the left of where the video came in, and find the 3-pin connector that is the negative sync connector. You'll notice that there's a couple of diodes there and a little resistor capacitor network, but do you see how even if you put separate inputs into this, separate vertical and horizontal sync inputs, you see how they're kind of joined together anyway? They're kind of nailed together right underneath those diodes. Well, if you follow the wire down from where the two diodes are joined, and at the first node, remember the first intersection we call a node, hang a left for about a half an inch and straight down a couple of inches, left an inch, straight down, find transistor Q301. Q301. Q301 is the sync amplifier. I guess that makes that the sync amp, huh? The sync amplifier. This monitor, remember I said, is designed for composite sync. If you have a sync problem in this monitor, it will be doing both things at the same time, as I demonstrated. It'll be rolling vertically and shifting left and right, as I showed you before when I pulled the sync wire out. I've never seen this fail. As a matter of fact, I blew this transistor up in a monitor intentionally, trying to make a sync problem for a lab session that we had. The dang monitor still synchronized perfectly. I have absolutely no idea how that's possible, but it did. I mean, I blew the top off the transistor. It was gone. It was just 3 legs sticking up out of the board. There's nothing else attached to them. And the thing still synchronized perfectly well, so I don't know what the deal is there. I've never, ever seen a synchronization problem in this monitor. In fact, sync problems in general are very rare. Sync problems are very rare. It's possible. Anything's possible, but for some reason, I just never see them. Now, let's turn back and look at the sync circuit in the Electro-Home monitor. We're going to be shifting back and forth between these two, by the way, in case you want to leave it kind of more accessible. And if you look at this guy, this schematic diagram here, the sync circuit, look at the top of the schematic right up here, just to the left of where the color came in. It says H sync, V sync. That's where the positive sync comes into pins 5 and 6. We don't use that anymore. Look on the left-hand side where it says negative H sync, negative V sync. That's the little 3-pin connector. That's our negative sync connector. Well, what I want you to observe is this, or what I want you to notice anyway is this. Let's follow the negative horizontal sync in. From the left, it goes to the right through a resistor into X305. Everybody with me? Mike, you got it back there? Cool. The output of X305 comes off the collector, comes off the lead on the top, the lead without the arrow, and it jogs a tiny bit to the right and straight up through a small capacitor, 0.1 microfarad. Do you see how it goes into the base of X301 there? Well, that's the same place the positive sync came in. Do you see on the top of the page how the positive sync, horizontal sync, comes into the base of that transistor? Okay. Here's the deal here, and it's pretty important that you understand what I'm talking about here. This monitor was designed for positive sync, actually. The original design of this monitor was for positive sync only. And then we had to make it compatible with negative sync because at the time that Galaxian came out, if you've been in the business that long, Galaxian was negative sync. It's one of those first, I think the first Namco licensed game, actually, licensed to Midway. What X305 does is takes the negative sync in. It looks like that, a negative sync pulse. and inverts it, flips it upside down. And what comes out of this transistor is a positive sync signal, which is then run into the base of the transistor where the horizontal sync, the positive horizontal sync, came in to begin with. So this is X305, this is X301, correct? X301. And then this goes actually out to the integrated circuit, which we'll look at later on, that processes that sync. But if you recall when we did the transistor demonstration, as I increased the base voltage, the collector voltage dropped, didn't it? Remember that? More base voltage, the collector voltage dropped. Well, that's what's happening here. When the base voltage is up high here, it's down low here. As the base voltage drops, the collector voltage goes up. So this is a sync inverter. The reason I point this out is that on the rare occasion that you might have, on the rare possibility that you might have a sync problem, you would have to check both of these transistors, wouldn't you? In other words, it comes into this one first, gets flipped upside down, and then goes into this one where it goes into the rest of the circuit, whatever's going to be using that sync signal. Where on the Wells-Gardner, we just had the one transistor. On this monitor, there are two for each type of sync, two for horizontal and two for vertical. In the old days, when we had positive sync, there might be sometimes when this transistor wasn't even used, but in this case, all our games are negative sync, and so we'll be using both the transistors. Okay, so that's the sync. So far we've looked at the video circuit, the blanking circuit, the sync circuit. Let's take a look at the vertical deflection circuit. And turning your book to page 51, I think it is, 53, 52, 52.1. 52.1. Page 52.1. I had to add some extra pages to the book. You're a lucky group. You're the first group to get this brand new and improved big blue book of really swell technical information. Anyway, let's take a look at the vertical deflection circuit. This article, in fact, explains everything in the world you'd ever want to know about the vertical deflection circuit. Let's start out by taking a look at the drawing on page 52.8. And this is the vertical output circuit from this monitor. It's the vertical output circuit in this monitor, the Wells-Gardner 4900 series monitor. And the circuit starts out in an integrated circuit. It starts out, you see this integrated circuit right here on the drawing? This is where the vertical circuit starts out. It starts out in what we call the vertical oscillator. You see where it says vert OSC there? In the monitor, there's an integrated circuit. In fact, it might be prudent, in fact, at this juncture for me to show you the integrated circuit. Let me just do that.
See, good on the other one.
Yeah, but this is a different monitor. I'll show it to you in just a second. Down in here, there's an integrated circuit right down in there. That's it on this particular monitor. There's a similar circuit here in the Electrohome monitor. It's right here. It does exactly the same thing. Inside this integrated circuit, there's this thing called the vertical oscillator, OSCILLATOR. An oscillator is a circuit that generates alternating current. You give it a DC power supply, it makes AC. This is where the 60 cycles per second, or 60 hertz, starts out. Remember I mentioned that the frequency of the vertical deflection circuit is 60 cycles per second. And that's the same frequency as, our AC power plug down here. But it doesn't depend on the AC power plug to get that 60 cycles per second. It's generated internally in the monitor, and this is where it comes from. It comes from this vertical oscillator. As a matter of fact, when you are adjusting the vertical hold control on a monitor, here's the potentiometer, the vertical hold potentiometer. This guy's sometimes called the vertical frequency too, because that's what you're adjusting. When you're adjusting the vertical hold, what you're doing is adjusting the frequency of the vertical oscillator. You kind of get it in the ballpark, and the sync circuit comes along and locks it immediately in place. In other words, you can adjust it from maybe 50 up to 70 cycles per second. Somewhere in the middle is 60, and that's approximately where you want it. If, for instance, you had a problem where the picture was rolling, let's say, at 1 roll per second, like once per second it goes shh, like that. What that means is your vertical frequency is 1 cycle per second different than what's coming out of the logic board. Basically what that means. So that's where it comes from, excuse me, this vertical oscillator. Well, the vertical oscillator isn't powerful enough to drive the yoke, the deflection coil in the yoke. It has to be amplified. And so inside this integrated circuit, you also see that there is this vertical amplifier also inside the IC. Well, to be honest with you, we don't really care that much about that. You can't get inside the IC to fix it anyway. Let's take a look then at the vertical output circuit. And the vertical output circuit's over here on the right-hand side of the schematic. Let's take a closer look at it here. Turn backwards, back to page 52.3. And let's take a more abbreviated look at the vertical output circuit. And the first thing you see is the vertical output transistors, the 2 vertical output transistors. Very common failure. Not at all uncommon. Very common failure. You'll notice that there is a dashed line around these things. That means that they're mounted on a heat sink. It means that they're mounted on a heat sink. If you turn to the next page, you'll see it's very easy to identify the vertical output transistors because they come in TO220 packages in pairs mounted on heat sinks. So it's real easy to identify them. Let's take a look at them. They're right here. Very easy to see. 2 transistors, TO220 packages, mounted on heat sinks, and don't forget what it says right there. That's really important. Okay? 話は街道を受け止めしたいってそうからさ手めたいそうか And what does that mean? That means danger. So that means danger. And the reason it says means danger is that these transistors can get hot. But also, normally, there's no insulator behind these things. I don't know if somebody put that in there or what, but normally the heatsink itself has some voltage on it, so you got to be careful about that. But there they are, 2 transistors, and yeah, they've been changed. See that? This is not. I told you that they fail sometimes. This is not original equipment. This is one of those NTE parts I was telling you about, like ECG parts. Same thing, an NTE 375. This is the original part, 2SD 1138. Let me mention that, by the way. I forgot. I didn't mention that before. You see how the part number on there is D1138? The real part number is 2SD 1138. You can see the little Hitachi logo on that. All the Japanese transistors start with a 2S. So when you're looking them up in your ECG book or a replacement guide, if you can't find it under D1138, you would look it up under 2SD1138. So there they are in the Electrohome, and in the Wells Gardner 4900 series, a little more difficult to spot. They're down here, mounted on the heatsink. I can't really show it to you. You can clearly see the heatsink though. There's the heatsink. Kind of difficult to actually see the transistor. It's down in there somewhere. We're going to get back to page 52.3 in just a second, but I'd like you to turn back to the whole full-blown schematic on page R34, because I want you to make a note on your schematic about a common problem. Find the same circuit on this monitor schematic, and it's right in the middle on the bottom. You see the two vertical output transistors, they have the dashed lines around them. It's really the exact same circuit. Right above Q302, there's a resistor here, R313. Find that and circle that on the schematic diagram, because this is a common failure. Anyway, this resistor is right here on the board. It's this one that's mounted vertically. See this guy right here? What happened was they ran out of real estate on the board. See that? And there was no place to mount it, so they had to mount it vertically like this. Well, this resistor is in series with the whole vertical output circuit, isn't it? If you look, the power supply lines at the top, it's 130 volts, goes through that resistor, then into the two vertical output transistors. When that resistor fails, what does it do? Does it short circuit or open circuit? Always open circuits. In other words, instead of 470, oh, here you go, Dan. Instead of 470 ohms, you've got, 12 million zillion ohms. Heads up. Oh, what a shot. All right. And as a result, you get no power to that section. And in fact, what you end up with is a very thin picture. I don't think it's just a line. I think it may be about an inch tall or something like that. The reason that it fails is that because of the cockamamie way they mounted this resistor, like this, all the heat travels up the resistor. I heard someone mention dissipation. That's true, and it just gets real hot, and eventually it just cracks and open circuits. So this is a fairly common problem on this particular monitor. When you have a problem on the Wells-Gardner 4900 series, and you just have a line across the screen or a very narrow, very short picture, check that resistor. That's a fairly common problem. But if it isn't that, if it isn't the resistor, I always check the resistor first in this monitor because it's much more common than the transistors failing. The resistor opens more often. If it isn't the resistor, check the two vertical output transistors, see if they're okay. If they're okay, my next step would be to replace the integrated circuit. By process of elimination, there's really not much left in the circuit. Let's go back to that page 50, whatever it is, 52.3. Sorry, 52.8. This is the entire circuit. This is the entire thing. And there's not much in the way of active components here. There's the two vertical output transistors. There's a couple of other diodes in here. I've never seen these diodes fail. And then there is the integrated circuit itself, and a few other resistors and capacitors. I have also never seen this IC fail. I'm telling you that if I changed the transistors or checked them and they were good and it still didn't work, I would just change the IC to see if that's what the problem was. I've never seen it fail. Ever, never, ever. Not in this monitor. I have in other monitors, though. In other types of monitors, they have almost exactly the same circuit. In fact, the vertical deflection circuit's very similar in almost every monitor. The transistors were good. The IC itself was bad. Not very likely. It's really the same kind of theory as we used when we were working on switching power supplies, where if we had a problem and it wasn't the diodes or something like that, we would simply change the integrated circuit and see if that's what it was. And this is basically the same thing. There's no clear-cut way to test the integrated circuit. Instead of poking around and trying to figure out what the heck's going on, since you can poke around for half an hour and still not know what you're doing, but change the chip in 10 minutes and know exactly what's going on, that's the easiest thing to do. By changing the chip, you've changed hundreds of transistors at once. So you might as well just do that and see what's going on. Now, what I'm about to go over now will enable you to fix 50, 60% of all the monitors you come across. And in fact, this is so common, there's not a week that goes by in the shop that I don't fix vertical deflection problems that are capacitor failures. We use lots of capacitors in monitors. There's tons of them. We discussed the little capacitor kits that you can get from Zen and Electronics to replace all the caps in the monitor. When you have problems with a distorted picture, where the monitor is working basically, but the picture somehow looks distorted, I can guarantee you're talking capacitor failures here. By distortion, what I mean is like pictures where the top of the picture is squished and the bottom one's stretched out. Sometimes the top is so squished that it appears to be actually folded over, and you see a little bit of the image upside down and backwards on the top of the screen. Common problem in the old Nintendo monitors, where the top of the picture just plain squishes. C407 goes bad, 10 microfarads, 160 volts. Real common problem. And all these weird kind of distorted problems, where you look at the monitor and the sides are maybe curved, or the top is squished, the bottom stretched out, or something like that. All of these are capacitor failures. We have lots of capacitor problems in monitors. Let's turn back to 52.3 here. And I want to point out one such capacitor to you. If you look at Q1 and Q2, the two vertical output transistors, kind of smack dab in the middle, actually from the emitter of Q1, there's a line that goes straight out to the right, straight down to pin 3 of the yoke connector, and it goes into the vertical deflection coil in the yoke. This is the output of the vertical circuit. The output of the vertical output circuit comes from the junction of the two transistors. You follow that out to the right, it goes straight down through the vertical deflection coil in the yoke. Now we're at pin 4. Follow that up and to the right, and do you see the capacitor labeled C2 here? That is our return path. Remember, we have to have a complete path for electric current to flow. It comes out of the two transistors, shoots through the yoke, and comes back, and it's got to get to ground somehow, and it goes through that capacitor. That capacitor is often a 100 microfarad, 160 volt capacitor. You want to remember that value. This is a real common failure. That's the AC return cap. All of the current that goes through the yoke has to go through that capacitor. When that capacitor fails, it doesn't work like it should. Not enough current goes through the yoke, and the picture starts to shrink. This happens over a period of time. It gets smaller and smaller, you keep adjusting it, it gets smaller, you keep adjusting it, and finally you can't adjust it big enough anymore, and the picture's only a narrow band across the screen. As it fails, it also causes the picture to distort. Usually the top squishes. When I have a problem with vertical deflection, where the screen is not filled out completely from top to bottom, or distorted, meaning squished at the top usually and stretched at the bottom, the first thing I do is I find an electrolytic capacitor that's 100 microfarads, 160 volts, or at least I look for it, and change that first. It's the first thing I change. It fixes about half the problems. Yeah, Ken?
So that holds true for all brands of monitors?
Many brands of monitors, yeah. I'm really surprised. When it finally dawned on me that I've been replacing the same value a bunch of times, I thought, oh my God, this was really true, that there's a mess of different monitors out there, and most of them use this same value, which is really cool. It may be, as you see on this page, 1,000 microfarads at 35 volts, depending on the monitor that you're looking for. There is another value that I see quite often that fails in the vertical circuit. Let's, wait, stand by just one sec. Let me take a look at something here before I tell you where to turn. Yeah, turn to page 52.8. And there's another couple of values. Find capacitor C308. It's if you look at the top vertical output transistor, go to the left an inch or two, and down just a skosh, and there is C308. It's 3.3 microfarads, 50 volts.
Yeah.
This is another common value that I look for. There are two values that I find fail very often in vertical circuits. Not being an engineer, I'm not sure what they do, and I don't really care. I just know that they fail a lot, and that's all I care about. One of them is the 100 microfarad, 160 volts DC. That's a cap I always carry with me. I've always got some of those. I mean, unless I've used them all up, but I'm pretty sure I still have some. Then the other one is either a 2.2, 3.3, or 4.7 microfarad capacitor, depending on the monitor that it's in. Another real common failure at 50 volts DC. I see this one a lot, and this one also causes lots of weird distortion, mainly squished at the top and stretched out at the bottom kind of distortion. But I see this value all the time. There's another one that might fail in the same monitor, connected to pin 3 of the integrated circuit, 2.2 microfarad. That's another one. Connected to pin on page 52.8, pin 3 of the IC, straight down, 2.2 microfarad. But here's the deal, really. In a monitor, by the time a capacitor is going bad enough to cause a vertical deflection problem, distortion of some sort, all the caps in the monitor are probably on their way out, really. And it is very prudent at this juncture to replace all of the electrolytic capacitors in the monitor. It's one of those few places in electronics that we can do preventative maintenance. In electronics, other than blowing the dust off, there's really not a whole lot you can do in terms of preventative maintenance. I mean, if you've ever been in the service, they do something called PMS, and that's a preventative maintenance system, they call it. And they go through stuff periodically, like on a ship. They'll pull all the floorboards off and vacuum underneath and clean everything off and blow it all off, and it all looks, ship shape. But we really, other than blowing dust off and stuff, there's not much you can do, except in this case. Electrolytics, as I mentioned before, fail eventually, 100% guaranteed. If one's starting to go out, you might as well change them all. And so that's basically what I do. When I get a monitor in the shop that has a vertical deflection problem, some kind of distortion in the vertical circuit, First I start out by looking for these two values, the 100 microfarads and the 2.2, 3.3, or 4.7, and they may physically be located anywhere. What I usually do to look for them is I start where the vertical output transistors are. Easy to find because they're two in pairs on TO220 packages and all that. I start working my way out in a radius, looking for electrolytics as I go out. Or I'll start where the yoke connector is. There's a connector that connects the yoke to the chassis. Start there and work your way out physically on the board. Just start changing electrolytics. And what you'll probably find is you'll change one maybe and the problem will get a little bit better. You'll change another, it'll get a little bit better. Then you'll find the one that's really bad and the problem will go away completely. But heck, as long as you're sitting down there with your soldering iron and the monitor's out and everything, you might as well get a bag of capacitors from Zanan Electronics and replace them all at once. The first time you do one of these kits, it'll take you about an hour probably to find them all, and you're very cautious and everything. The second time you do one, it'll maybe take you half an hour, and then it's about 20 minutes per kit, really. It's really a good idea to replace them. As I mentioned before, the other reason you want to know about Zanan Electronics is that this guy Aubrey Jones, that is Zanan Electronics, is Mr. Monitor, and he'll help you out on the phone tremendously. You can always give him a call. He's happy to help you out. He's a real nice guy, and I strongly recommend that you do business with him. If for no other reason, then you can pick his brain, And it's here on page 82 in your book, Zanan Electronics, 3109 2nd Street, Lubbock, Texas, 79415. The phone number, area code 806-793-6337. Tell them Randy Fromm sent you. Ask for that big 15% Randy Fromm discount. Thank you.
Keep those pledges coming in.
Keep those pledges coming in. All right, my friend, dear friends, let's fix a monitor. Thank you.
Oh, did you want to mention something about how that one part is screened backwards on those?
Mm-hmm. It's in the thing anyway. So.
It's in the kit.
It's in the kit, yeah. So vertical deflection problems are very common. That's the deal. The point I'm making is the monitor's up high in the game where all the heat rises, the electrolytics dry out, there's a lot of electrolytics in the vertical circuit, and the vast majority of my vertical deflection failures are taken care of by replacing vertical output transistors and replacing electrolytic capacitors. About half my monitor problems are that. Okay, everybody cool? Make sense? All right, well, so far we've looked at the video, the blanking, the sync, the vertical deflection. Excuse me. The power supply in a monitor is a regular standard series pass regulator power supply, just like everything that we went over before when we went over the regulator section of the class. I'm not going to go over that again because it's exactly the same. And remember, I pointed out to you the helping hand resistor on the monitor, an excellent place to check the power supply voltage. Remember, you're going to ground the black meter lead, measure the voltage at one side of the resistor. Should be whatever your B plus is supposed to be, like 130 or 120 or whatever. On this monitor, it's this large white resistor here. On the 4900 series, it's this guy right here. Right down there. A lot more difficult to get to in this monitor. It's not this one. It's this one down here. It's usually 15 to 25 watts. This is just a 10 watt one up here. Same thing. One side of it is, I don't know which side is which. One side's the unregulated output, input. The other side's the regulated output. Honestly, don't know which side is which. I don't care.